In this video, we're going to take a look at the hypothesis testing of proportions. So, it's a case where we want to make a claim about a population proportion, and we want to set out to find evidence to support that claim. An example could be that a company could be saying that it believes its market share has changed from, say, 30%. It believes now it has changed or it has actually increased. So let's just consider the case of increase. If it says increase, then we are looking at values greater than 30%, 35, 38, 40, 42, just values larger than 30%. If we had said that we believe it has changed, it could be worse, it could be better. So it could be 35, 40%, or it could be 25, 20%, values that are smaller. So we often want to test situations where the population parameter involves a proportion. We could be hypothesizing about the proportion of the student body that is international students. One point in time, it may have been 15%. What is it now? Is it now 20%? So we could hypothesize that it has actually increased significantly. So that brings us to hypothesis test proportion. The procedure is pretty much the same, except for one thing. The test statistic is different because we're dealing with proportions now. Always remember that the test statistic is a function of the sampling distribution. So since we're talking about population proportion, the sampling distribution is the sampling distribution of the sample proportion. And so our Z value, in this case, which we typically would assume that the sampling distribution of the sample proportion is normal, that Z value is based on proportions, not the mean, but proportions. So, hypothesis test for a population proportion. The null and alternate hypotheses are stated in terms of the population parameter. In our case, we'll be using pi. So everywhere you see p, remember pi. Sample statistic is p bar. The null hypothesis should be a statement concerning the parameter that includes the equality. We know that. We should have something like HO. Pi is equal to some value. Let's just use some value v. Or pi is greater than or equal to some value v, or pi is less than or equal to some value v. So any one of these situations, but the equal sign must be in the null hypothesis, HO. Okay? The significance level of the hypothesis determines the size of the rejection region. We've been through that before. The test can be done on a one-tail or two-tail depending on the alternate hypothesis. So in a case where if our null hypothesis say that pi is greater than or equal to a value, then the alternate would say that pi is less than that value, which means that it's a one-tail test in the left, less than. Think less in the left. And then if we say if the null hypothesis says pi is less than or equal to a value v, then that means in the alternate hypothesis, we'll be saying that pi is greater than that value, which means that we're looking in the right, greater towards the right. And then in the null hypothesis, if we said pi is equal to v, then in the alternate hypothesis, we'll be saying pi is not equal to v. So if it's not equal to, we want values higher or lower, in which case we have a two-tailed test. So a hypothesis test for proportion, if you recall your data types and that proportions have to do with categorical variables, essentially you have a binary situation. Either you have an attribute, the desired attribute, or you don't. So we could say you're an international student or you're not. You have, if we're looking at grades, students who perform well versus students who don't perform well. Well being maybe say a B and above or a B plus and above. We could decide what that is. So we have two situations. People wearing red shirts and not wearing red shirts. Items are defective versus not defective. So we usually describe it in terms of success and failure, which comes out of the binomial distribution. All right? So the procedure is 1, specify the population parameter of interest. That is what we do when we're testing for the mean as well. Specify the null and alternative hypothesis. Then specify the significance level, alpha. And remember, significance level is the maximum risk of committing type 1 error. It is also the size of the rejection region. Construct the rejection region for one-tailed test. Determine the critical value Z alpha. If it's a two-tailed test, it would be Z alpha over 2. And then we could then go ahead here for the two-tailed test. We have these two values right here. One is negative and one is positive. Then step 5, we compute the sample proportion from our data. Sometimes it's given to us. And then we compute the test statistic Z. Reach a decision by comparing the observed value, Z observed, to the critical value, to Z crit, and or by comparing the p-value to alpha. P-value concept is also the same. If we obtain our Z observed, so if it is a one-tailed test, it could either be PZ greater than or equal to Z observed if it is a right tail, or PZ less than or equal to Z0 if it is a left-tailed test, or it could be twice PZ greater than Z0 if the value occurs on the right, or if it occurs on the left, it would be twice the probability of Z less than or equal to Z0. So, or we could have sort of written it out this way. It would be PZ greater than or equal to Z0 plus PZ less than or equal to Z0. Okay, so we'll calculate the p-values in that. And here is a simple example. A league is considering increasing the season ticket prices for basketball games. The marketing manager is concerned that some people will terminate their ticket orders if this change occurs. If more than 10% of the season ticket orders would be terminated, the marketing manager does not want to implement the price increase. So, what happens? We're going to state that, oh, no, we're not going to lose anybody. We're not going to have more than 10% of people actually terminating the orders. So we will assume that our null hypothesis is that it is the less than or equal to 10% will actually give up the ticket orders. And then we'll make the alternate hypothesis that the true proportion is greater than 10%. We have 5% significance level. We've been using 5%, but it could be different. It could be 2.5%, it could be 1%, it could be 10%. And then we have a sample of 14 in 100, which is basically 14%. Our critical value, because it's a one-tailed test, with 5% in the tail, is 1.645 for the normal distribution. Okay? And in case you're wondering how we got that, well, just draw the diagram. Put 5% in the tail. If this is 5%, find the Z value. You should know how to do that by now, which means that you got to find this polka dot area and go to the table and find the Z value. So Z is 1.645 in this case. And we would go ahead and calculate the Z value. I'm looking for the Z value here. It's not here. So let us figure what that is.